Now let's talk about the mole concept involving volume and molar volume. We talked about how this formula comes about in our introduction to the mole concept, so it would be advantageous if you watched that video and then came back to this video for you to be able to understand everything. Make sure you also watch part 1 of this series, because in that series we talk about the first part of this video. Now, we came to this conclusion because of the Avogadro's law. And the formula that came about was N is equal to volume of a gas divided by the molar volume. And now the molar volumes are these numbers. Molar volume at RTP, which is room temperature and pressure, is 24 cubic decimeters. At standard temperature and pressure, we have got 22.4 cubic decimeters. These two conditions have been explained in the video about the introduction to the mole concept. So it's a must watch if you want to understand everything the right way. So N can be sometimes abbreviated just as N is equal to V over mv, where V is the volume and mv is the molar volume. What you should note is that the volume will be in cubic decimeters. What this means is that if the volume is not in cubic decimeters, you need to convert from the unit it's in into cubic decimeters. Let's talk about some examples for you to understand how this formula can be useful. We know the formula is N is equal to V over mv. So let's talk about a question that just shows us how we can use that formula in the simplest way. This question is a perfect one. They are telling us carbon monoxide and oxygen are reacted in a laboratory. At the end of the reaction, 48 cubic decimeters of carbon dioxide is produced. Find the number of moles of carbon dioxide produced. It's a simple question. We're just using the exact formula that we're just from looking at. N is equal to V over mv. As you can see, we're still using the same steps. Those 4 steps will be just like a guide for us to work in mole concept. They are not like rules that you'll find everywhere, but they are very good steps that you should take when answering a question about the mole concept. So now we know the formula we're using. The next thing is to see if we have enough data. So we have the volume, it's given 48 cubic decimeters. Now, what is our molar volume? They haven't told us whether to use RTP or STP, so how can we figure it out from the question? In chemistry, when you're told something was done in a lab, just remember that a lab is a room. So the molar volume in a laboratory will be 24 cubic decimeters. Now, since we have identified the needed data, we now need to check if the units of the data are correct. Is the volume in the correct units? Yes. Well, then we can solve our question. N is equal to V, which is 48 divided by 24. If you know some math, you can do this mentally, but I won't take it for granted. I'll calculate it. 48 divided by 24. You can see it gives us 2. So N is equal to 2 moles. Nice and easy. Let's talk about example 2, where things become a bit more complicated. In this example, we've been told 220 grams of a gaseous compound, which is X oxide, or simply we can refer to it as an oxide of X. This compound occupies 120 cubic decimeters at room temperature and pressure. Now we're asked to determine the molar mass of this oxide of X and thereafter identify the element X. We're talking about volume, but you can see there's mass here. So why have they given us the mass? Okay, later in this example, you'll see why the mass will be very useful. But you know, since we're talking about volume, the formula we'll be using is N is equal to V over mv. But in such a question, what you just need to think about is this. If I use the formula which involves masses, can I find my number of moles? We have the 220 grams in the correct unit and it's given to us. But can we find the molar mass? Notice that X is not an element found on the periodic table, meaning we don't have it. When we notice this, this is an indicator that we won't be using the first formula right from the start. We have more information about volume and molar volume than information about the masses. Therefore, we are going to use this formula and we have identified in step 1. Step 2 is looking at the question if we have any data that we can use. Obviously, there's the 120 and the RTP, which indicates our molar volume is 24. We had number of moles equal to 5, as you saw in our calculator, and we're headed the right direction. Notice that we haven't yet found the molar mass of this oxide of X. Right now, you might be thinking, well, that's not the question. Well, this is the right way to go about such questions. Remember that at the beginning, I told you you should be able to know even the relationships between the formulas. Under the more concept, as you can see, it's saying more concept. So it's a way of working with the more, or a concept of working with the more. By this, I mean, under the more concept, when you find the number of moles, like n, we used this formula, right? But we can take this n and plug it into another formula which can enable us to find the molar mass. So MR will be equal to m over n. I'm sure you recognize this formula. We derived it some time back. M is 220, the number of moles we found in another formula. But because we found the number of moles, that n will be applicable in any of the formulas we pick. Even in that same first one we looked at in the introduction to the more concept. Meaning, in more concept, you might be even asked to find the number of particles in such a question. So 220 is going to be divided by the number of moles, which we found as 5. So this oxide of X has the molar mass of 44. Now we're going somewhere. We found the first question in this example. Determine the molar mass of the oxide of X, or simply X oxide. This compound has the molar mass of 44. It means we can identify the element X. Just like we did some time back when we were talking about the first formula, we can do even now. If we can find the expression for the molar mass and equate it to this 44, then we can find the element X. So our job is finding how many atoms of X are present here. You can see that's 2. The atoms of oxygen, there's just 1. Here we don't have the atomic mass of X, so I'm just going to abbreviate it as X. You can select any letter, but X will be more natural because X is the unknown here. Now we go for oxygen. Oxygen's atomic number, I'm sure we've been using it quite often in this video. You know it's 16. 2 times X gives us 2X, and so we're going to add 2X to 16. Obviously, you know we can't add a number with a variable with just a regular number, which is a constant figure. So we're going to have this expression 2x plus 16. Now, remember that if we have the molar mass of this compound, and then we have this expression which represents the molar mass of this compound, I hope that's not a lot of explanation, but simply what I'm saying is that if this is the molar mass we've just found here, and this was the molar mass we found by this formula, we can equate these two things. And then we can subtract 16 on both sides, or just take this positive 16 over to the other side of the equal sign and becomes a negative. So 2x will be equal to 44 minus 16. So 2x is equal to 28. Now, it's just a matter of finding half of 28, because what this means is that in this 28 we've got 2 atoms of X. Therefore, if we want to find 1 atom of X, we're supposed to get rid of that 2 there. We'll divide both sides by 2 like that. Cancel the 2 here because it's not serving us any purpose. I multiply by 2 and then again I divide. Nothing done, so I just cancel that. So X is equal to 28 divided by 2. Again, you can do this math without a calculator. 2 into 2 is 1, 2 into 8 is 4. So the atomic mass of this X, just 1, is 14. Now, if the atomic mass of this element or atom is 14, if we go on the periodic table and check the elements that are found there, we can find one of the elements that has got the atomic mass 14. And if we find that element, then we found the element X. As you can see, that element is nitrogen. It looked impossible, but now